In this video, we're going to look at an example of graphing a polar equation. Let's consider the equation r equals 2 plus 4 cosine of theta. And the first thing we want to do is sketch a graph of this in the theta r plane. Recall this would be a cosine function that has an amplitude of 4 and then has been vertically shifted upward by 2 units. It would look something like this. This graph is going to be used to tell us the length of a radius vector when we graph it in its polar coordinate system. Two of the places that are particularly important to find are when this graph crosses the theta axis, since this is when our radius is going to be a length of 0. It would be when our graph is at the origin. To find the places where we cross the theta axis, let's set r equal to 0. We can solve this for the cosine expression by subtracting 2 and then dividing by 4. It would give us a cosine equals -1/2. On the interval 0 to 2 pi, there are two values of theta where cosine is -1/2 at 2 pi over 3 and 4 pi over 3. At these two locations, these two angles, we know we're going to be at the origin. Of course, these two angles live in the second and the third quadrants. For any other angle, we're going to have a non-zero radius. For values of theta, or for a value of theta of 0 radians, we could note that our radius would be at 6. And so at 0 radians, which would be in this directions, a radius of 6, 1, 2, 3, 4, 5, 6, would be starting right here. Then, as we rotate through the first quadrant up to pi over 2, then our radius vectors are going to be described by the y values, or the r values, on this graph. And so they would always be positive, but getting shorter, until eventually at pi over 2, we'd have a radius of 2. So when we construct our graph, it would start over here at a radius of 6. It would rotate through this first quadrant until at pi over 2, it's at 2, which would be about here. And so our graph might look something like this. As we rotate from pi over 2 to 2 pi over 3, so right here is pi over 2 to 2 pi over 3, which where we have an intercept, our radiuses are still going to be getting smaller, but eventually getting to 0. And so our graph, as we rotate through this area, will get smaller and smaller. Our radiuses will get smaller and smaller until we're eventually at the origin. After 2 pi over 3, as we rotate through towards the angle of pi, our radiuses are going to be negative. And they're going to be getting longer until they're longest at an angle of pi, where they'd be at -2. But at pi, a radius of -2 would reflect about the origin to about right here. And so as we rotate from 2 pi over 3 to pi, our radius vectors get longer and longer and longer, but in the negative direction. So rather than being in this second quadrant, they'd reflect to the fourth quadrant, and they'd be over here. From pi to 4 pi over 3, our radius vectors are still going to be negative, but getting shorter and shorter until eventually the radius is 0. So as we rotate through this third quadrant, our negative radius vectors would reflect to the first quadrant and get smaller and smaller. It would look something like this. At 4 pi over 3, our radius is 0. We're at the origin. After 4 pi over 3, our radius vectors are going to get longer and longer until eventually they get to 3 pi over 2. At 3 pi over 2, our radius would be a 2. And so on our graph, as we rotate from 4 pi over 3 to 3 pi over 2, our radius vectors are going to be getting longer, eventually hitting 2. So as you rotate through this quadrant, they'd get longer, eventually hitting 2 at 3 pi over 2. After 3 pi over 2, as you rotate through this fourth quadrant, back to 2 pi, as you rotate from 3 pi over 2 to 2 pi, our radius vectors would be getting longer and longer, eventually being longest at 2 pi, where the radius would be 6 again. So our graph, as we rotate from 3 pi over 2 to 2 pi, our graph would be getting longer and longer, eventually hitting back to our starting point at 6. And this is the graph of the polar equation 2 plus 4 cosine of theta. I hope this is helpful, and we'll look at another example in another video. We'll see you next time.